Oops, I guess I'm recording to the cloud. Okay, so today we're going to work on the week 7 handout. I think it's a leaf blower outside. I don't know if you can hear it. If you can, I apologize. All right, so handout 7. So this is for the inner automorphisms and automorphisms and things along these lines. Problem 1 we already did, right? Like I did problem 1 actually as part of lecture. So we probably don't need to worry about that too much. Problem 2 is very easy. It's trivial. Problem 3, let's see if we can just answer this right now. Does anyone know what the answer is to problem 3? Right? Like without trying to do any work, let's just do it right now. So problem 3 says, why is my pen not working? I swear it's only this class that my pen hates. So problem 3, it says, if you take U20, so if our group is the group of units on Z20, find TG for all G and G. Like, actually, I guess a better question is, what the hell is TG? I think it was defined in the book. I originally thought it was just conjugation, but now it actually occurs to me it might not be. But either way, U20 has 8 elements in it, right? So I'm not computing this for 8 things if it's not trivial. But let me just pull that up just to be certain. Where am I looking? 301 book. Yeah, what did he call TG again? Does anyone know what TG is supposed to stand for? It's very mysterious to me. Right, so phi sub G were the inner automorphisms. What was T sub G? Oh, here's some T sub G. Oh, and Cayley's theorem. Oh, it's just left multiplication. I see. Right, so U20 here is what? What are the elements of U20? So remember that the elements that are co-prime to 20, right? So 1, 3, not 5, 7, 9, 11, 13, not 15, 17, and 19, right? There should be 8 things there. There are. T3, right, is going to be the map from U20 to U20, which takes X to like 3X, right? It's just the left multiplication action. And yeah, what is this thing, right? And I'm not going to do this for all of them. You can just write them out if you really, really want to. Just compute what it is that this thing does. And voila, you're done. So I don't think there's much sort of like interesting stuff to do here. So we're not going to worry about problem 3. Now, problem 4 is where it gets interesting, right? So like I said, problem 1 is trivial. Problem 2 is trivial. Problem 3 is just grind it out. You don't need me for that. So problem 4 is where it gets interesting. So suppose that phi is an automorphism of the multiplicative group of real numbers. Right? So again, that's the set of real numbers. You remove 0 because 0 doesn't have a multiplicative inverse. And if you included it, you wouldn't have a group. So we're going to take the real numbers, we're going to throw R away, and then we're just going to say, yeah, under usual multiplication, show that basically phi preserves signs. All right? So that is, if X is greater than 0, then 5X is greater than 0. And if X is less than 0, then 5X is less than 0. And really, the theorem says more than this, right? Or I guess the problem, not the theorem. It says to prove that these are true, but it turns out that this is the same thing as what I wrote down. Okay. And yeah, let's see if we can solve that. So I'm going to give you, I don't know, how long do I want to do? Let's do 8 minutes, because this one can be a little bit tricky. But let's do about 8 minutes on this. We'll see if we can solve it, and then we'll come back. I'll run you through it. And this is going to be the only problem we do today, so we might even break early, right? But yeah, like I said, 8 minutes, and then don't hesitate to scream in the chat or come on mic or something if you have any questions about it, and I'll go into it in a little bit more detail or give you hints, because this is the sort of question that, like, once you have the right hint, it falls apart very, very quickly, right? So let's try that, and in 8 minutes, we'll take it up. Here, boom, resumed. Okay, so let's see how you did. Now, the critical trick here is to say, okay, I need something which basically preserves signs, right? Like knowing that this thing is an automorphism, what do we know about it? So let's see. So solution, I actually found a couple of other cool things when I was doing this problem. So solution though, so immediately note, since phi is an automorphism, so in particular it's a homomorphism, right? Since phi is an automorphism, what does that mean? So that means that phi of AB is phi of A, phi of B for all A and B in the multiplicative reals, right? Because multiplication is the group operation. Okay, now the really nice and kind of critical thing that, if you recognize this, then the whole rest of the thing falls apart, is basically, well, what if I let B be equal to A, right? So thus, for every A in R star, phi of A squared is phi of A, right? And that's phi of A squared on the outside, like that. Okay, and that number, right, phi of A squared has to be greater than or equal to 0, but in fact, it has to be strictly greater than 0. Can anyone tell me why it can't be equal to 0? Right, why can't phi of A squared be equal to 0? Why can I say it's strictly positive? Right, exactly, right? 0 is not a possible option in the codomain, right? Our inputs can only be non-zero real numbers, and our outputs can only be non-zero real numbers as well. So yeah, absolutely, we can't have 0 as a possible output option, right? So if it's greater than or equal to 0, but it can't be 0, we know it's strictly positive, right? All right, so what I'm going to do, now the kind of weird thing about this is I'm not actually going to show these two things are true. I'm going to show something slightly different, and it will be equivalent, but we're going to have to think about it for a little bit in order to convince ourselves. So basically, the thing that I'm going to use is the following. So suppose A and B are disjoint, as are C and D. Okay, so these are all disjoint. F is just any function from A union B to C union D, right? If F of A is a subset of C, and F of B is a subset of D, I guess I should say F here is a bijection. Actually, I don't think it matters. We'll check that in a second. So if F of A is a subset of C and F of B is a subset of D, yeah, let's say is a bijection. Then in fact, they are equal. And F of B equals D. Okay, so does everyone believe this theorem, right? Like basically, if I can write the domain as the disjoint union of two sets, and I can write the codomain as the disjoint union of two sets, and there's this like perfect correspondence, A maps into C and B maps into D, well, they're not actually subsets. They have to be equal, right? And the benefit of this is basically that I don't have to prove the reverse inclusion of the two things that I circled above, right? It'll actually be enough to show that the image of 0 infinity is a subset of 0 infinity, and that the image of negative infinity to 0 is a subset of negative infinity to 0, right? So do we believe this? Is everyone okay? Do you see that this is true? Do I need to explain it a little bit more? Because I'm happy to explain it. But I mean, if everyone here is just like, oh yes, this is obvious, we don't need to go into it more, right? So it's okay. And basically, like if you actually want to prove it, I'd recommend doing it by contradiction, right? So you would say, well, let's suppose that there's something in C, because my function is bijective, right? So everything in C comes from something in A union B. And can it come from something in B? No, because everything in B maps to D, not to C, right? Okay, so this is true. And if you want to prove it, it's like 2 lines of a contradiction proof. So assume that it's a contradiction. So for us, this means that it's sufficient to show that we have subsets, right? We don't actually need to show equality. We just need to show inclusions like this. And this is nice because you know how we always harp since 102, we're always like, oh, you got to do double subset inequality. And it's true, most of the time you do. But if you're clever about it, then you don't have to, right? Because again, here, right, what am I saying? We know that R star is the disjoint union of these two sets. And so this is precisely this result, this result that I have in white above, right? Where in, you know, like A and C are the same set and B and D are the same set, but we're trying to use the white result. And if I can prove that these equations are true, then we're done, right? So all I have to prove is that the top thing is true. So let's try that. Okay, so let's start with this one. So let's show that phi of 0 infinity is a subset of 0 infinity. And to do that, of course, we're going to start with something on the left-hand side and show it's in the right-hand side, right? So let's say let x be an element of 0 infinity, right? So we want to show that phi of this is in 0 infinity. Is there an obvious way to do this without contradiction? I think we might just have to do it with contradiction, right? So for the sake of contradiction, suppose phi of x is negative, right? Okay, now I said kind of the key point here is this fact right here. Let me just put it in a big old square rectangle. Okay, so if I look at phi of a squared, I always get a strictly positive number, right? So I've started with a strictly positive number. Maybe let me try and keep that on screen. I've started with a strictly positive number. And I've assumed that its image is negative, right? That phi of x of this thing is strictly less than 0. Is there any way that I can use the green rectangle at the top of the screen to get a contradiction here, right? Like, is there some way that I can write x as something squared? Right? Because if I can write x as something squared, don't we just need the square root of x? And then we don't even have a contradiction? Okay, this is interesting. So let me, first of all, let's use the square root of x. Let's try that. But, so it depends on what you mean. Oh, I see what you're saying. Oh, okay, sure, yeah, let's do it. Yeah, I like your proof better. Let's do yours. Let's not even do a contradiction. And if you're doing a contradiction, you just do the same thing. But you're right. You're right here. We don't actually need a contradiction. Let x be in 0 infinity. So that phi of x is phi of the square root of x times the square root of x, which is the phi of the square root of x squared. And that has to be strictly greater than 0. You're right. And we should avoid contradiction if we don't have to use it. So you're absolutely right. I do like yours a little bit more. So let's do it that way, right? And so now we've shown that phi of x is in 0 infinity, and that gives us exactly what we wanted, right? So thus, phi of 0 infinity is a subset of 0 infinity. Beautiful, right? Okay, for the other direction, what do you want to do? Because we have to show both of them, right? So I either need to do a double subset inequality on this problem, or I have to show that negative infinity 0, its image lies in negative infinity 0, right? And so by the theorem that we just said, I would rather do that. Okay, so let's do the same sort of thing. So pick x in negative infinity 0. So we want to show that phi of x also has to be negative. What do you want to do? Sorry, that was probably a little bit loud. Don't reinvent the wheel. What do we do? So we already know something, right? We already know that this is true. Can we use that again? If I wanted to reuse this fact, what would I do? Okay, so my problem here is that x is in negative infinity to 0. Yeah, something with negative x, okay? So if x is in negative infinity to 0, then negative x is in 0 infinity. We all agree, right? Right? That's definitely true. If I give you a negative number, you take the negative of it, it's now positive. So that's true. So that means that phi of negative x is in 0 infinity, right? But phi of negative x, that's the same thing as phi of negative 1 times phi of x. Well, I guess if I write this a little bit like that, times phi of x like that. And what do I want here? Let's make sure that this makes sense. Yes. Is phi of negative 1 equal to negative 1? Right? I'm pretty sure that it is. Yes. Yeah, because this is the only element that has order 2, right? We can prove that more detailed in a second, but that's equal to negative phi of x, right? And so I've got that negative phi of x is in 0 infinity, so phi of x must be in negative infinity 0, right? And I'm done. So voila. So now I've proven both of those things that are true. And I'm done. Okay. Excuse me. All right, so any questions? Do you all see that 5 negative 1 has to be equal to negative 1? Should I go through that? Right, okay. So let's talk about that. Okay, so basically we need that phi of negative 1 squared is equal to phi of negative 1 squared. But if I write that as phi of 1, That has to be 1, right? Because it's a homomorphism. So the identity has to map to the identity. And 1 is the multiplicative identity in the multiplicative real numbers, right? So I have that phi of -1 squared must be equal to 1. So there's only 2 options for phi of -1, right? Do you agree? That makes sense? Pranav, I see your question. I'll come to it in a second. Okay, and why can't it be 1? Bijectivity, exactly. And phi of -1 does not equal 1 since phi is injective, right? We already know that phi, like basically its kernel has to be trivial. This would be a non-trivial element in the kernel. Alternatively, remember, isomorphisms have to preserve the order of an object, right? The only order 2 elements, or there's only a single order 2 element in the multiplicative group of the reals, and that's -1, right? -1 is the only number such that when you square it, you get 1, and that 2 is the first number where you do that, right? So obviously, the order of the identity is 1, and so the identity has to map to itself. So the only element of order 2 is -1, and so if you have an isomorphism, the order 2 identities must map to each other. There's only one of them, so -1 has to map to -1. Does that make sense? So that was another way of seeing it if you want, but if you go through this proof, maybe it's a little bit more clear. Okay.